So, hello everyone. This example is actually based on your week 6 lecture. I mean, the one that I've uploaded, right? So, remember, in under your week 7, the video, I have already explained to you until example 1 under definition 1.8. So now we are looking into your second example. You can find these notes in your week 6 lecture. All right. So in example 2, we have xt equal to xt minus 1 plus at, right? And we want to show whether this is non-stationary or not. So here, say if we have a second equation, okay, now from here, from the main equation, if I'm writing it as xt minus 1, that means this one will become 2, this would be minus 1, right? So that is exactly what is being written over here. Okay, so once you're done with this, if let's say you substitute this whole equation into this, okay, you will be getting this. Okay, and if you continue to do so, at one point, you will reach x null and then you will have A1 until A T. Okay, if you continuously do this, right? So if let's say we take our x null as 0, so this one 0, you are left with only A, right? Okay, and your A is following this, where your mean is equal to 0 and your variance is equal to uh, variance is constant. Okay, so to check whether it's weakly stationary, we need to ensure that your mean is constant and your your covariance does not depend on your time, right? So when you find the expectation, I think by now you should be able to do this. Okay, this whole thing will be equal to 0. Okay, and then to do the covariance, okay, remember in the previous example we have t plus h and then xt. You can do it in this manner or you can do it like this, also not a problem. Okay, as long as you're comparing it with two different values here, t, like if I put here as 1 here as xt, not a problem. Okay, so here you're actually looking at your lag x, what autocovariance s lah, because it's from t until s that you're looking at. So here, why we have a summation is because when we are finding t here, right? Variance of t will give you from variance of 1 a1 because your x is already gone until variance of at, right? And this would give you t time because this one is all happening for t times. Okay, so t times the variance because it's sigma square will be t sigma square. Okay, so if this one continues so quite a number of times, that's why we have the summation of ai here, where I is equal to 1 and until t. And then we have your xs also, right? So this one would become from 1 until s. This is j. Okay, so this is the summation of both of them, lah. Okay, which would give you the value here, st sigma square. Okay, so if let's say your t here is greater than s, that means it would be s multiplied by variance square. If it's lesser than s, then it's t times variance square, right? If it's equal to each other, okay, if like this one ij, if this is I means this one would be equivalent to 0, and your variance here, if it's not equal means it's not related, right? So it would be 0. If it's I just like what we did before, like covariance z earlier, right? This one would give you the sigma square in this case. Okay, so that's why here you have sigma square lah. Okay, so if you notice, the second criteria covariance here actually depends on your time because the S and the T here is time. That is why this particular process is not stationary. Okay, so I hope you get a clearer picture already on how to determine whether a process is weakly stationary or not. Okay, this is quite important for you to know. Now moving to your main lecture, the lecture notes. Okay. Yes, so this is what we have just covered. We have already done example 1 and example 2. Okay, now if you see the second 1.9 here, 1.9 actually is talking about your lag K is defined by this. Okay, so lag K, if you notice just now I had the gamma, I mean covariance XT and then uh, XS, right? So that would become gamma S. This is equal to this. Okay. Okay, this one is becoming more specific because it's giving you an addition here, lah, T plus S here. So the lag K here is actually giving you the time difference. So if I, again, to make it more specific, if I put S, this one would be T plus S lah, in that case. So if I put here as 1 means this one will be plus 1. So what this is giving you is the extra. So if I put here as 2 means this one will be 2. Okay, all right. So this is the to meet the weekly stationary criteria, it has to only depend on the K. And this is actually known as the autocovariance function. Okay, this is quite important for you to know, especially because it's needed to find your autocorrelation function, this thing. Okay, so remember in your previous lecture, you have seen the ACF plot many times already by now, this one. Okay, so whatever that is being calculated here is actually your autocorrelation. So autocorrelation is your autocovariance for K divided by null. Okay, right? So this one please keep in mind. Right, so these are all general properties, something that we will be learning in the later on chapters on how to use this. So the first one is the gamma null is greater or equal to 0, and then your absolute value of your gamma K is lesser and equal to gamma null. And then your gamma K is equal to negative K, gamma negative K, which means that if you have here 1, right, it is actually equivalent to negative 1. Okay, similarly for the ACF function, this one we have already covered in the previous lecture already. Remember in the ACF also I said, right, you need to be very careful with the lag. So if here is 0 means because PK is equal to this autocovariance equation, right? So if it's in sin null, so this is gamma null over gamma null, which is equal to 1. So that's why this is always equal to 1. Okay. Number 2 and 3 here are similar to the autocovariance function. Okay, now this one all I will give you all some time to go through, but I will get straight into the examples later on, this thing. Okay, then okay, and then even for the weekly stationarity, you can go through this. All right. Now, from the mathematical tools, before the models of Box-Jenkins are considered, these are the 3 main concepts that is very important in time series: the backward operator, difference, and generating function. So backward operator is very important because of its notational convenience. We will be looking at this in your autoregressive model, in your ARIMA model. Okay, all right. So it's mainly this is the property that we are looking at. Okay, so okay. I'll get into the examples later. So this operator is always used for your polynomial form, and it can be summarized in this manner here. Okay, where phi b is equal to the summation of all of these backshift operators here. Okay, and then we have the covariance generating function. Okay, so also something that we will go through. Okay, no worries. The linear differences. Okay, so I'll just go to the example now. This example is also attached in the, oh, sorry, is also provided. It's in the week 7 notes, week 6 notes. Sorry. Okay. All right, so this is under the mathematical tool. So if um, we will go through what type of a model this is later on. So to follow the backward operator, you just need to move this to the other side. That means you group all this is your current observation, this is like your previous observation, okay, plus the white noise or the error term here. So if let's say we move it here, right, it would be given in this form. So we are actually looking into the observations in this case. Okay, so the backward operator is applied for these observations. Now you have a phi here, right? So when you move it here, your phi will have a B here. I will explain this in more detail in the later on chapter. Okay, so if you see in your lecture note, in your lecture note, if you see Bx t is equal to xt minus 1, t minus 1. Okay, so that's why this part here. Now, if let's say you have yt minus 1 means, then this one will also be b yt, right? Okay, so since you have a phi here, now here will also be a phi. Okay, so that's how this one here, after you move it to the other side, right? So the yt will be minus, this will become this one. So be yt equal to at. So if you factorize your yt, you are left with 1 minus phi b equal to 80. Later on, you will understand why it's very convenient to have this backward operator. Okay, so in this case, the function of your backward operator will be 1 minus phi b. I'll give you another example here. Let's say if I have xt is equal to 2. For example, okay. Sorry, this one A2 A2. Okay, so again, these are all based on previous observation, right? So if you move it to the other side, you have xt minus 2 xt minus 1 minus 3 xt minus 2 equal to 80, correct? Okay, so again, your bxt is equal to xt minus 1, right? Based on the previous in your lecture note. So if I have a 2 here, means this side will be a 2. Okay, so this part here, this one here will become 2bxt. Okay, if I have a minus 2 here, means based on your notes, it would be a square. So now you have minus 2 here, right? So this one would become square and this will be 3. So this will become minus 3b square xt. Okay, equal to a t. So if you simplify this further, it will be given in this. So now you can understand, you might have an idea um, that this part here is a bit more convenient than looking at it like this. Okay, all right. But we will get into this part in more detail when you are studying the autoregressive and ARIMA model. Okay, so if you have 3 here means then here will be power 3 lah, and so on. Okay. All right, so this is the first part that you need to keep in mind, right? Another one, this one I will explain to you when I'm getting into the ARIMA, the AR model. Okay, it's much more easier to compare later on. Okay, so but for the time being, it would be great if you can try to understand this thing here, the C power of K here. Okay, because this one is actually relevant to this one here. Okay, quite simple to understand. Okay, so back to the notes. Okay, we are almost there. Okay, so the autocovariance function, okay, don't worry about this. Okay, linear difference equation is the one that I've just explained. Okay. All right. This one, also don't worry too much about it. I will get back to you on this with more examples for the next part. For this syllabus, we are only focusing on case 1. Okay, we'll look into when it's real and distinct. Okay, but you have another 3 more cases that you can go through on your own. These real and equal, unrepeated, complex conjugate, and then you have repeated complex conjugate as well. Okay, all right, so that is all for this lecture, right? Thank you.